Today we are going to discuss the second part of LS and JJ coupling. In the last lecture I briefly discussed LS and JJ coupling and did a problem. In this part I will be doing a few more problems so that the concept about LS and JJ coupling is clear. So let us get started with the first problem. So this is the first problem of today. So the problem is let me just so the outermost shell. So the problem is the outermost shell of an atom of an element is 3d3. Show that the spectral symbol for the ground state is 4f3/2, assuming LS coupling. So we are assuming LS coupling and then we have to find the ground state. So basically we have to remember the Hund's rule. So we have to find, so for Hund's rule, so first is maximize S. So we have 3 electrons. So the maximum S can be, the spin quantum number can be 3 into half, that is 3/2. So what about L? What are the orbital quantum number? Like I had done in the last class, in this case, so here you have something like this. So we have the d subshell or orbital. So you can 1, 2, 3, and you can just name them. -2 is corresponds to Z component -2. This is -1. This is 0. This is 1. This is 2. So 3 electrons. So you can have them like this. Okay, this is a possibility. So this corresponds to ml is equal to -3, or you can have something like this. So again I divided into 5 compartments. There we have, and then electrons can be like this, and one can go here. So -3 plus 1. So this corresponds to ml is equal to -2. So like this we can show that the possible values of ml range from -3 to through plus 3. So that means L is equal to 3. There is only one option is equal to 3. That's why written L is equal to 3, and the ground state here is minimum J, because this subshell is less than half filled. So minimum J is given by 3 minus 3/2, which is 3/2, and hence the answer. Okay, so that is it. So yeah, so that this takes care of everything. Multiplicity 4, F, and this is 3/2. Now go to the next problem. Next problem, there are 4 electrons. So there are 4 electrons in the 3D subshell of an isolated atom. Show that the total magnetic moment in the ground state is 0. So same principle. First we have to maximize S. So 4 into half, that is 2. And here L is equal to 2. So you have 4 electrons, like I have done just now, you can convince yourself by placing the electrons that here in this case ml can only take the values -2, -1, like this. It can go to 0, 0, then +1 and then +2. So that gives us only one option, L is equal to 2. So minimum J is given by 2 minus 2, and that is 0. So what is the Lagrange factor in this case? It is 2. You can check. The Lagrange factor is 2, because here L and S are the same, and so mu J is minus J Lagrange factor, mu B Bohr magneton, and this is the magnitude of the total angular momentum, root J into J plus 1. So J is 0, hence 0. We go to the next problem. So here we have to use the Landé's interval rule, which we had discussed in the last class. So the separations between the adjacent levels of a normal multiplet are 22 centimeter inverse and 33 centimeter inverse. So this is proportional to energy. 33 centimeter inverse means the energy difference here is greater than the energy difference in this case. So assuming that the LS coupling scheme is valid, use Landé's interval rule. Show that the J values of the multiplet are 1, 2, 3. So it is given, we know from Landé's interval rule that Ej plus 1 minus Ej, the energy difference between successive multiplets is actually A times J plus 1, where A is a constant, and here it is 33. And Ej minus 1, so this is the energy difference between the multiplets denoted by J and J minus 1, and that is equal to A times J, that is 22. From there you can easily calculate these two expressions. You can calculate what is J. In fact, you will find J is 2, and from there the answer is obvious. This is the problem on JJ coupling. So here the number of terms arising of JJ coupling of a 3s and 4p electron. So what will be the number of terms? And here is JJ coupling. So 3p, so 3s electron means here J1 will be, so S is 0, L 0, and spin is half. So there is only one option for J1, that is half. In the second case for 4p, L is equal to 1 and electron is spin constant by half. So there are two options for J2, half and 3 by 2. So the combinations can be half and half, or half or 3 by 2, and from there I can get the values of J. So here, from here I should get what are the possible values of J. So here what we get is the values of J for this level. For this split we will get 0 and 1, and for here it will be, we will get the values of J to be I think 1 and 2. So obviously the answer is here 4. So here the answer will be 4. The number of terms will be 4. Okay. So we go to the last problem. The ground state electronic configuration of titanium is argon and then 3d2 4s2. Which of the terms below is not a valid spectroscopic notation in this case? Now this is about D2. If you remember, D2 equivalent. This is about D2 equivalent electrons. This is about D2 equivalent electrons. Okay, because of this. This is not important because this is fully filled. So we have done all this case. We just have to go back and see which are the terms which are there. So if you just go back, so these are the terms. So we can just go back and see. We have done this before. You can see 1s0 is there, then 3p0 is there. What are the terms they have given? 1s0 is 3p0, 1d2. So 1s0 is there, 3p0 is there, 1d2 and 1f3. So 1d2 is also there, but 1f3 is not there. You see f is here, is no. So obviously this term, so which of the terms below is not a valid spectroscopic notation? Here this is not the, so the answer will be this one. This is not a, so this is just just go to the red. So the value is, this is the answer. This is not a valid spectroscopic notation. So we'll stop here today, and very soon we will meet with the next topic under atomic and molecular physics. Thank you.